let me first answer a question uh, a student asked before we actually go into the lecture. So Vihanger asked a question. If we have to check the transistor is properly biased or not, is it enough to draw one load line, AC or DC? Or is it necessary to draw both of them? Um, the point which I fail to understand is how to get the variations of the Q point with AC input. Does the AC load line change with time? Like in the figure, there was a figure. Right, so that was a good question. Let me try to answer that question before we move on. Let me share the screen. Okay, so you guys can see my screen.
Yes, sir.
Thanks. All right, so let me go to this page. All right. So the question was basically regarding the load line, and what he wants to know is whether the load line changes with uh, AC input, right? So load line is nothing but so the transistor characteristics, so we can obtain between VCE as the x-axis and IC as the y-axis. Now note that I have drawn simple I capital C and simple V capital C, which means AC plus DC, right? Uh, and the DC load line is when the AC component is 0, that is when VCE IC, okay? That's between IC and VCE. So let me draw it in red. That's my DC load line. This value will be my VCC, and this value will be VCC divided by RC. If you have an RE also, that will also come into the picture, right? So let me call this RE also. So whatever is in the emitter, collector emitter uh, total line, right? So loop. So this is my DC load line. On that, I select an operating point, which we call the quiescent point, Q point. That is basically VCEQ. So remember, these are all capital, and ICQ. So these are DC quantities, right? So this is the Q point. Q point, or the Q point by definition is a DC point, right? When there is no input applied to the circuit. So this is a AC. There is no AC component when it is operating at this point. On the other hand, when you draw the AC load line, for example, if this RE is in, so for example, in a circuit like this, I'm only drawing the collector emitter circuit, right? So if you have something like this, and if you have a bypass, emitter bypass like this, then in the AC load line, the slope will just be RC, right? 1 over RC, right? So therefore, my AC load line, in fact, would be something like this. So this is my AC load line, right? So that's the slope is only RC. So slope minus 1 over RC. Whereas in this DC load line, slope will be minus 1 over RC plus RE. Okay, so this is basically what you have, and both these pass through this Q point. AC load line, by definition, its origin is at the Q point, right? Right. So this is basically what you have. Uh, but when there is a, a signal applied to this, right? When a signal is applied to this, when a signal is applied to this, so obviously this should be properly biased. And when a signal, AC signal is applied to this, right? So what happens? Okay, let me. So what happens is when there is a source voltage or the input voltage is applied, it will increase the current. So when you have more current, more voltage, the VBE will increase, and thereby a larger current, simple IB, will be added. Simple IB uh, from this side will be added, and that will be multiplied by beta to obtain a simple IC, right? So there is already an IC, capital IC, the DC value. In addition, there will be a small value. So therefore, in this case, since the current is added in the same direction as the DC voltage, the current will increase when you increase the voltage. So if I draw the current waveform, the current would increase with the input voltage, like that, around this Q point. This is the current waveform. So this will be my simple IC plus this is ICQ. So that will be 0 axis. So ICQ, IC plus ICQ. So that will be total voltage would be like that. So therefore, when this moves like that along this, let's say for example at this particular point, it corresponds to that point in the AC load line, and this point corresponds to this point on the AC load line. So if you want to look at the output waveform, output with time, if time goes in this direction, and this is my voltage axis, so this is increasing VCE, right? So this is VCEQ, and this is 0 volts. So that's my VC T axis, right? So this will be the DC axis, right? That is when there is no current. But when you change this current like this, when it goes from here to there, the point moves along the AC load line from here to there, and therefore at that point the voltage varies from here to there. Okay, so it would be varying like this. So that is my output voltage. So at this point it will be here 1 2 1 2 1 2. Okay, so this is basically what you have. So therefore when you apply a voltage, what will happen is the signal will move along the AC load line like that, along this. Okay, so while the Q point is still the same because it is the AC, it's the DC point, operating point, the instantaneous operating point will move along the AC load line up and down. Now, why is this important? When you bias it, if you select this VCE to be half of VCC, right? If this is equal to 1/2 of VCC, the issue here is because the AC load line has a greater slope, while this side you can have an AC signal increase up to VCC divided by 2 roughly, minus a certain amount due to the saturation. So this is the saturation line. Let's say this is like point uh, this is like 0.2 or 0.5, it's roughly about 0.2 volts VCE, and also the cutoff, this is the saturation, and the cutoff is something like, again, a small current like that. This is the cutoff, right? So the maximum it can move is in the positive direction. In the positive direction is this direction, positive VCE direction. You can have only from here up to here, whereas in the other direction you can go all the way up to there. So what actually matters is that this distance is equal to this distance. Okay, these two distances has to be equal so that you can have the maximum swing. Otherwise, now what happens if this is not guaranteed? You will have, so obviously the saturation point, so the distortion will occur right here. Okay, so you can have this way, it's fine, but it will distort this way like that if you don't have equal amounts. This is assuming this side is VCC divided by 2 minus 0.2, but this side is less than that because of this slope difference. Okay, so that is why you need to actually look at the AC load lines, where it cuts the VCE axis, and divide that by 2 roughly in order to get the Q point, right? But obviously Q point at this point depends on the Q point also, so therefore it's kind of you need to move it along this line and get it. So roughly you have to make sure that this side and this side are not equal. This on the DC axis they are not the same when you have a bypass capacitor like this, right? Hopefully that is clear. And now, Vihanga, was it clear, Vihanga?
Yes, sir, it's clear.
Okay, thank you. All right, let's get back to our regular lecture then. Any other questions you guys have? Let me know. Okay, this is where we stopped last time, right? So we were looking at the feedback concept. We said that feedback concept is not just applicable to circuits or amplifiers. This is a more general concept in engineering, where therefore we looked at it as a more general block diagram where voltages or currents were indicated as X. So X can be a voltage or a current. Xs can be a voltage, but X out can be a current, depending on whether you have a what type of amplifier you have. Transconductance amplifiers, transresistance amplifiers, change the type, right? So anyways, by applying this feedback, I think there is one line missing here. Okay, so like that. So we define these things, and we when we stopped it, we said the loop gain is defined as beta A. Why do we call this the loop gain? Because the open loop gain, when you don't have this feedback, right? When you don't have this feedback, then in that case what you have is only forward like that, right? Like that. So therefore uh, so forward gain is just this, nothing else. There is nothing changing this. So therefore forward gain, we call this open loop gain, which is equal to A. The feedback factor, in other words, gain in the feedback network, is this value here, beta, right? In this direction, what is the feedback? What is the gain, right? So X naught, and if let's say X naught is a voltage, XF is also a voltage, and xf can be obtained by, let's say output is like this. So the transistor output is like this. You take a voltage divider and take this value. Okay, so this R1 to R2, so that may be my output. So therefore this will decide the feedback factor. So the beta is like R2 over R1 plus R2. Okay, that is, you have V out here, Vf, which is equal to R2 over R1 plus R2 V out. Now in this case you see beta is that much. Okay, now do not confuse beta with the beta value, the current gain of a BJT. So we beta, I think it's a this beta in this is a standard notation in control systems applications. That is why we use this as beta. Otherwise, we could have used a different notation to avoid any confusion with the beta that we use in uh, transistors. Okay, so do not confuse with the beta of the transistor. Okay, so it's not HFE. Okay, so don't confuse with the HFE. HFE value beta is not what we are talking about. This beta is something like R2 over R1 plus R2, some resistor ratio, something like that. No, not necessarily this. It can be different for different types of topologies, but all what you need to remember is that this is not the beta that we used to talk about in transistors. This is for not just necessarily for transistors. This is for control systems in general. Okay, so therefore if you go around this loop, this this loop like in the green color line, the total gain around this is beta times A, times actually negative 1, because you have a negative sign here. So if you go around the loop, that will also come into picture, right? Sometimes therefore we mark it as the negative value of that. So loop gain, we call this the loop gain, is equal to beta times A, which we call the notation that we use is T. Sometimes we also use loop gain to be minus beta. Okay, so keep that in mind, right? So that is the loop gain. An amount of feedback, the amount of feedback is written as 1 plus beta A. Okay, so this is by we divide or multiply different quantities by this. We'll look at it later to obtain a certain value. So for example, the gain with feedback, we call this closed loop gain, right? Open loop gain is without feedback. Closed loop gain, closed loop gain, right? That is with feedback is equal to, if you remember, A divided by 1 plus beta A. Okay, you see that the gain, open loop gain, is divided by the amount of feedback in order to get the closed loop gain. Often beta is a small value, much less than 1, maybe 0.1, maybe 0.01, maybe 0.5, some value. It can be even 1. Of most of the time it is less than 1. But A is the gain typically is very high, right? We start with a high gain amplifier. So therefore beta is very stable. Beta is obtained using a resistor ratio or something like that. So beta does not change. Remember, this is not the transistor's HFE. So therefore beta is typically obtained using a resistor ratio, something like that. So therefore they are very stable. Whereas A, amplification, the open loop gain, very high, typically 50 or 100 or even more sometimes, but it is not constant. It varies with various other things. Like for example, it varies with temperature. For example, a typical value would be A may have a variation between 50 and 200, a very large variation, right? But when we design a transistor amplifier without feedback, it may vary the voltage gain depending on the temperature or some other variable from about 50 to 200, so which is not reliable, it's not repeatable. So but if you apply negative feedback beta, then you will we will see later that since A is large, we can make this independent of A. All what we care is that A should be large. Then we can show that this closed loop gain will be roughly equal to 1 over beta, right? This will be equal to, so if this is equal to, let's write this again, is equal to, if I divide top and bottom by A, this will be 1 over A plus beta, right? So 1 over A is very large. If A is large, if A is very large, greater than 1, then this can be roughly equal to 1 over beta, right? So this is completely independent of A. The gain of it's only dependent on beta. Beta, remember, was less than 1, so therefore 1 over beta is greater than 1. So if I make beta is equal to 0.1, my gain will be 10 instead of 100. Maybe A was initially 100. Now I make beta, I use 1/10 of it, 1/10 of the output, and feed it back to the input. Then 1 over beta is 10. So my gain goes from 100 to 10. So the gain is reduced. But we are going to see that though the gain is reduced, there are so many other things that improve. For example, the sensitivity of gain to other external factors like temperature is going to be very, very low. Right? We are going to analyze that in a minute. Okay, so let's move to the next page. Okay, so this negative feedback, we call this the negative feedback. Negative feedback properties. So we mentioned this earlier also, but let me state them again. Negative feedback properties. This number one is desensitized gain. Gain is desensitized. Desensitized gain. What that means is gain is less sensitive to circuit components variations of circuit components. Okay, so for example, beta value. If beta varies, the sensitivity to when beta, let's call this not beta, let's call this HFE. If HFE changes, the gain does not change much by applying negative feedback. If it is not there, if HFE changes, the gain will change. Okay. The second one is reduced nonlinear distortion. Reduced nonlinear distortion. What that means is output is proportional to input. Output is proportional to input. Or constant gain independent of the input value. Okay. Constant gain independent of signal value, signal level. So signal can be 0.1 millivolts or 10 millivolts, the gain will be the same. Okay, that's what we mean by. So if you plot the input output characteristics, this will be something like this. Instead of initially, it may have been something like this. Instead of that, we don't now have non-linearity. It will be like this. Okay, so that's what we mean by input non-linearity. Number 3 is reduced effect of noise. Okay, any the effects of noise will be reduced. Now, obviously, the gain is less, so therefore the noise will also be amplified less. Okay, number 4, reduced. So control input and output impedance. Control, I don't say increase or decrease, because we can make it either increase or decrease depending on the topology, right? Sometimes we would like high input impedances, sometimes we like low input impedances. For example, if for a voltage amplifier, we like input impedance to be higher, but for a current amplifier, we would like the input impedance to be lower. We can use feedback concept to either increase or decrease the input impedance, right? So that is what we mean. Control input and output impedance. By applying appropriate topology. We'll see what these topologies are next. Okay, this also extends bandwidth. Okay, extended bandwidth, which means if I had a gain of 100 from, let's say, 10 hertz to 100 hertz, now I will have reduced gain, let's say 10, amplification of 10, but now the range of frequencies that will have 10, it will be maybe like 1 to 500 hertz, something like that. So an extended range of bandwidth, right? So that is basically what. Now, all these are achieved by trading off gain, right? Gain has to be reduced from 100 to 10, some other value. Okay, all of these properties. So all the above properties are desirable properties. We like to have all these properties. Can be achieved by trading off gain. Gain. Okay, that's the thing that we trade off to obtain above things. Okay, now let's see the first thing, the desensitivity, right? So gain desensitivity, let's have a look at what that means. We'll analyze it and show that actually it happens. Okay, so gain desensitivity. Gain desensitivity. Now assume beta is constant. Now this is a very reasonable assumption because beta is not the transistor beta, HFE. This is typically a resistor ratio. So whether the temperature increases or decreases, maybe the resistance value may change, but both resistance both resistors, these values will change. So therefore, the ratio beta is very stable most of the cases, right? So assume beta, the feedback factor, is constant, right? So this is a very reasonable. This is not, beta is not equal to, this beta is not HFE, right? Beta is typically obtained by a resistor ratio, like R2 over R1 plus R2. Okay, so therefore this is a very reasonable assumption. Okay, this is a very reasonable assumption. Typically beta is less than 1, typically, right? Now if that is the case, we can write the closed loop gain that is gain with feedback, which we obtained as A divided by 1 plus beta A, right? Now if A is very large, okay, if A is very large, we showed this earlier, we ACL is equal to 1 over A plus beta roughly is equal to 1 over beta, right? Does not depend on on um, the active network A. The active A is a property of the active network, the transistor. Okay, so this is active network is what what A depends on HFE, right? Heavily depends on HFE, but this does not. Okay, so therefore this is stable. All it depends on is beta, which basically depends on resistors. They are very stable. Now if you want to mathematically analyze this, we can do what we can do is we can take the derivative with respect to A, dACL over dA, which is basically you can show that. So this is what you need to derive, take the differential with respect to A. You'll have A times, so you will have 1 over 1 plus beta A times the derivative of A 1 plus, in fact minus A times the derivative of 1 over 1 plus beta A, so that is why the negative sign, divided by 1 plus beta A squared times beta, what is inside, so something like that. So this will be 1 plus beta A squared 1 plus beta A minus beta A is equal to 1 over 1 plus beta A squared. So that's my dACL over dA. Okay, so if that is the case, dACL is equal to dA over 1 plus beta A squared. Now if I want to find the desensitivity or sensitivity, sensitivity is defined as dA over dA over A, right? Desensitivity or this sensitivity. Okay, so the closed loop sensitivity is equal to dACL over ACL, which is equal to this is equal to dA over 1 plus beta A squared. So that is dACL divided by ACL, that is A over 1 plus beta A. Okay. That's basically what you have. So you can cancel one of these terms here, and you will have this as dA over A times 1 over 1 plus beta A. Okay. What is this component here? This is the open loop sensitivity. This is the open loop sensitivity. Okay. But we know beta 1 plus beta A, beta is slightly small, A is very large. So 1 plus beta A is a large number. So 1 over 1 plus beta A is a very small number, right? So therefore, what's going to happen is, so this is called, this 1 plus beta A is called D sensitivity amount. D sensitivity amount. So what? So the open loop gain, or the DC gain is equal to open loop gain sensitivity divided by a large value, the desensitivity amount, right? So therefore, obviously, you can see that the gain variation, how much it varies with different factors, will be much less. Okay, the sensitivity is much less because you are dividing by a large number, 1 plus beta A. Is this clear, guys? Hello.
Yes, sir.
Okay, thank you. All right, so let's move on. Uh, let's move on to, so that's basically all we are going to talk about these feedback properties. Next, we'll move on to a new subsection, feedback amplifier topologies, right? We'll talk about feedback one minute, please. Feedback amplifier topologies. So depending on your type of input signal, it can be a current or a voltage, and depending on the type of output, it can also be a voltage or a current. You knew that there were 4 different types of amplifiers: voltage amplifiers, current amplifiers, transconductance amplifiers, and transimpedance amplifiers, or transresistance amplifiers. Depending on that, what you have as the output and what you have as the input are different. They can be either a current or a voltage. So therefore, when you sample the output, if it is a voltage, you have to sample it in shunt, right? You have to take the voltage as a using a voltmeter. So you connect it between the output terminals, so in parallel. So we call this shunt feed. You shunt sampling or parallel sampling. So it's a voltage sampling. If it's a current, you have to sample it using an ammeter kind of a thing, right? You have to measure it using an ammeter kind of thing. So therefore, it's a series sampling. So the sampling side, getting the feedback, is done as a shunt sampling or in parallel to the output if it's a voltage, as a series sampling or uh, if the output is a current. Okay, so the sampling is either shunt or series depending on whether its output is a voltage or a current. respectively. Similarly, if you want to add a feedback signal, if you are going to add negative feedback, so that you basically have to subtract. If the input signal is a voltage, you have to subtract a voltage from the voltage. You cannot subtract the current from a voltage, right? If the input signal is a voltage, you have to convert whatever the output into a feedback form which is compatible with the input type. So the same type. If the input is a voltage, you have to subtract a voltage. Even if the output is a current, you need to convert that into a voltage, and then only you can subtract a voltage from the voltage, right? So therefore, if you have an input type of voltage, always you need to subtract a voltage. In other words, you have to subtract as a in series. You have the whole voltage, you have to get out from it. So it's a series. You cannot connect a network in parallel and subtract a voltage. So if you are going to subtract the voltage, it's kind of like when you have to have a voltage drop somewhere else. Okay, so in the series, so you have to in series subtract it. So the feedback is has to be series if the input type is a voltage. Similarly, if the input is a current, you cannot subtract a voltage. You have to convert the output into a current and subtract it. How do you subtract a current? You have to draw a current from the current that is being applied to the input. You have to take some out. This we have to do using a shunt connection, right? In parallel, you have to connect something in parallel and draw something out, so that it's taken out from what is being supplied to the input. So therefore, that has to be done in shunt or parallel. And so the currents, when you apply the feedback, has to be connected in shunt. If it is a voltage, in order to give the feedback, you have to mix it in series. Okay, so that is basically the principle that we are going to use. Okay, depending on input signal, that can be voltage or current, to be amplified, and the output, again it can be a voltage or current. Amplifier can be classified into 4 categories, right? You remember the 4 categories: voltage amplifier, current amplifier, transconductance amplifier, and trans resistance amplifier. Depending on the amplifier category, one of four types of one of four types of feedback structures should be used. Okay, so what are these 4 types of categories? Now this is based on, if you want to feedback a voltage, feedback has to be series. If you have to feedback a current, the mixing has to be in shunt. Similarly, if the output type is a voltage, you have to sense it using a shunt connection. If it's a current output, you have to sense it using a series type of a connection. So these are the 4 categories, right? So type of, so we have type of mixing and type of sensing. Okay, so depending on that, we have the first type. If my input type is a voltage, so this is the input type is a voltage. If the voltage is what I have to, I am inputting the input signal is a voltage, then I have to mix it using a series connection, right? So therefore we use this series type of mixing. And if my output is also a voltage, this is the input out, this is the output out. Its output is also a voltage, then I have to sense the voltage using a parallel connection. Right? So this is called, parallel is called shunt type connection. So these kind of things are called series shunt feedback. Series shunt feedback. Okay. So the series is the mixing type, shunt is the sensing type. So mixing, sensing, feedbacks. Okay. So that's basically this. So this is a voltage feedback thing, uh, and you take the output as a shunt. The second type, if the input is a voltage, and output is a current. This is the second type. So this is a current divided by voltage is the gain. So for I over V, so it's a transconductance amplifier, right? For a transconductance amplifier, my input is a voltage, so therefore you have to mix it in series, but you have to sample it in series also, because it's a current. You have to sample a current in series, but you have to sample a voltage in shunt. Okay. So similarly, you can fill the rest of it as well. The current input and voltage output. So this is a trans impedance amplifier. Obviously, since output is voltage, you have to shunt sample it. Since it's a current, you have to mix it in shunt also. So these are called shunt feedback. Shunt feedback. And the number 4 obviously is when the input is a current and output is also a current amplifiers. So this is called shunt series feedback. Shunt series feedback. Okay. So these are voltage amplifiers. This is a transconductance amplifier. The third one is trans resistance amplifier. The last one is current amplifier. Okay, so these are the 4 amplifiers. For each of these amplifiers, you have to use a different type of a feedback structure. Okay, so let's look at the first type. What that means? It's a series shunt feedback. We use these for voltage amplifiers. So we use with voltage feedback, and you apply it in series with voltage. A voltage is applied in series. series voltage is output is a voltage, so you sample a voltage and apply the feedback in series. We also call this voltage series feedback. Okay, shunt series shunt is the same as voltage series feedback. It's a little bit confusing sometimes, so therefore stick with one. Maybe series shunt should be enough. Okay, these are also called voltage series feedback. Okay, so here in this case, this is the sampling, this is the mixing. Okay, this is the output, this is the mixing. Okay, so let me draw a series shunt feedback. So what you have is a voltage amplifier. So let's first draw that. So in the black box, this is my without feedback. I have a input impedance and a 7-inch output circuit. So this is my this is what I have in the circuit. So this is Ri input impedance. This is R out, and my gain is obtained as a voltage gain, which is multiplied by Vi, where this is my Vi and this is my V out. Okay, that's without feedback. This is the voltage amplifier. Now I want to apply a signal to this. So I have my voltage signal. This is what I need to amplify. So I connect it like that. Now without feedback, I would have directly applied it to this circuit. Okay, but now I want to apply um, negative feedback. Okay, so therefore I have to subtract this some voltage from this input voltage. Okay, I have to subtract so that this voltage should be in that direction. So that way I can subtract this. Okay, so that has to be in that direction. That needs to be kept in mind. And then I may have a load, which is basically a resistor in this case, which is connected because it's an output. It has to be connected like that, RL. So that is my output load voltage VL. Okay, so that is my V out or VL. It's like that. This is my load. Okay, I may have a current I in, which is this can be just a um, secondary factor, right? It's not something that we basically uh, know. It depends on many things. So therefore, when we need the feedback loop, this is my feedback network. What it does is basically it should sample the voltage, right? So therefore, it's nothing but something like this. So the same voltage that you have here applies here. The out has to be there, and the output of this should be a proportion of the input. That's my input. So therefore, this should be beta times V out. Okay, so that is equal to Vf. So this is Vf equals to beta V out. Now that has to be subtracted from my Vs. So therefore I have to connect it like this. Okay, so that this is positive, this is negative, so that it is in the opposite direction as Vs. Okay, so that way I can subtract Vf from Vi. So this is Vf. This is so Vi is equal to Vs minus Vf. That is the negative feedback. Okay, that way you can obtain this requirement. Now, for voltage amplifiers, what do you like the input impedance to be, low or high? We want high input impedance, right? And what do you want the output impedance to be? So that when there's a current, no voltage drop across the output, so the input or the output impedance has to be very low. So we require high input impedance and low output impedance. Okay, so we want these things. What do we actually achieve? In fact, using this feedback topology, feedback increases the input impedance. But actually, Ri with feedback is equal to 1 plus beta A times Ri. We can show this, right? In other words, because we have this additional thing, V in is reduced, so therefore the current has to reduce, right? Because you have a lower thing. So this total Vs is connecting to a kind of like a larger input. Similarly, R out in this case does not change. As you can see, there is no impedance here. But if there is an impedance between the output here, if this is there, then what will happen is it will the output impedance. So this is the input impedance looking at it from here, right? This is RIF, and output impedance is looking from here, ROF. Rout F will not change in this case because this is infinity. This is infinity, therefore it doesn't change. But if you had a finite value for this, what will happen? It will actually bring down the output impedance because anything in parallel will have the resistance will be less than the smallest one. Okay, so that's why it is so. Right, so that's basically the series shunt feedback. So we have about 5 minutes. Let me move on to the other one also quickly. One of the other ones, number two is series feedback. Series feedback or transconductance amplifier with current series feedback. With current series feedback, you apply a current, you obtain you obtain as the output a current. You take the current as the feedback signal, sensing the current and applying it in series because it's a voltage input, right? So therefore my circuit is a transconductance amplifier. So if I draw it as a black box, this is the transconductance amplifier. Okay, so again what you have is an input impedance, and output is a current. So therefore you have a Norton's equivalent circuit here. Right, so the direction, depending on what you want to mark, you can draw it in either way. This is, if you have a positive current gain, it will be in that direction. This is Ri, this is R out, this will be Gm times Vi, where Vi is this and my current is this, the total current I. That's the I out. Okay, so the feedback has to be given again as a, now input is a voltage source, so therefore my voltage source is this, in that direction. It has to be subtracted, so the direction of this should be like that. Okay, the feedback topology, so this is a feedback network. This is a feedback network, and I have my load. What is the load? Gain, a resistor, RL. Now this time output is a current, I out. The load current is going like that. Okay, so therefore I need to sample the current in series. Right, so this is the same current has to go through this. Okay, so this is the current like that, I out, and the output of this, let me call this like that, and output has to be a voltage. So therefore what I have here is a voltage source. Right, so this is Vf plus minus, this should be some beta times I out. I have Vf is equal to Vf is equal to beta times I out. Right, now I have to connect it to the positive side to this terminal, the negative side to this terminal, so that you subtract Vf. So Vi is Vi is again equal to Vs minus Vf. Right, so that is basically what you have. Right, now this has a transconductance amplifier. The input impedance has to be very high, output impedance also has to be very high, because it's a current source, right? So therefore I can write require high input impedance and high output impedance. Obviously the output impedance has not changed because of this, there is no change in this. This is a short circuit. If you actually have a finite value for this impedance here, then the impedance output will be greater than R out. So the resistance will add up. Okay, but R input obviously will increase, which is equal to R in 1 plus beta A. That again will increase just like before. Okay, so this is where we are going to stop today. So we see that input impedance has increased in both these cases, right? These are inputs are voltages. They actually prefer to have high input impedances, and we achieved it through feedback network. By connecting a feedback network, we were able to increase the input impedance. And obviously, this will reduce the gain, voltage gain in the first case, and the conductance gain, GM, in the second case. We will see that GM actually is equal to GM divided by 1 plus beta A, right? So GM is equal to 1 over 1 plus beta A, and in the previous case, A, so A V with feedback is equal to AV divided by 1 plus beta A. You should be able to prove this. We'll do that later. Okay, so this is with feedback. GM with feedback is equal to that. Okay, so we'll stop our class for today here. And if you guys want, you can actually try to derive the same things like this when you have series shunt, shunt and shunt series uh, topologies, right? All you need to do is make sure that your input is then the current source, and then you can replace this Vs with a current source Is and see if you can derive these same things. We'll discuss this next week. No, not next week, this Friday. Okay, Friday at 9 we'll meet and discuss this. If you have any questions, you can ask now. Any questions? No questions? All right. So, okay. So, since there are no questions, we can stop the class here. By the way, uh, if you guys can, I don't know if Mr. Aberatna is here. Aberatna, I haven't seen him for a long time. I don't know whether uh, there is an issue with him. If you have his information, kindly ask him to contact me. Okay, that is E15006 Aberatna IM. Okay, the batch rep.
Yes, sir, I'm here. I will tell him.
Okay, we can kindly tell him, right? Field rep. Okay, we can kindly ask him to contact me.
Okay, sir.
Okay, all right. Thank you. We'll stop the class here today. Thank you.
Thank you, sir.